everyone, and welcome to our session on data preprocessing part 3. Before we dive into models and predictions, we need to talk about something that often gets overlooked but is absolutely essential: preparing our data. Think of step as cleaning and organizing your ingredients before cooking. Without it, the outcome be a disaster. Today we will specifically focus on text normalization, techniques in NLP where the transforms messy unstructured text into a clean standard format that machines can work with effectively. So if you are ever wondered how a computer understands languages, this session is going to be exciting. Let's begin. Normalization. Why is text normalization important? Before we can apply any algorithm on text data, we must first prepare and clean that data. Text normalization is the first step in that preparation. Text data often comes from multiple sources: web pages, social media, chats, each using different formats, spelling, or symbols. Text normalization helps convert all of this into a standard format so that the machine learning models can interpret the data more accurately. Without normalization, the data can be noisy, full of inconsistent capitalization, punctuation, or slang. This noise affects the accuracy of NLP models. By reducing this noise, we help algorithms focus on meaningful patterns instead of irrelevant differences. In NLP applications like chatbots, sentiment analysis, or topic extraction, normalization ensure that similar words and phrases are treated as equivalent. This increases both efficiency and accuracy in processing natural language data. Different text pre-processing techniques. Converting to lowercase. Converting all character to lowercase, one of the first step in text normalization. The step ensure hello word, hello and hello are treated as the same word by machine learning models and text analysis tools. Text data can be inconsistent in casing due to user input, formatting, or system source. By applying lower, we standardize the text, improved token matching, reduce redundancy in the vocabulary, support efficient pre-processing for NLP tasks like sentiment analysis or search. Removal of URL. URL is a data rarely contribute meaningful insight during text analysis unless we are study links directly. In NLP tasks like sentiment analysis, topic modeling, or classification, URL act as a noise. The regular expression matches any substring that start with HTTP or www, followed by a non-white space character. It helps in removing most common URL format. These steps simplify the text and improve the performance of downstream tasks. Removal of HTML tags. When scraping text from website, we often get HTML like a division, span, etc. These tags do not carry semantic meaning in NLP task and need to be removed. Beautiful Soap is a Python library of parsing HTML, XML documents. The method .get underscore text exactly only the visible user friendly content from the HTML. The process ensures the only meaningful text is retained, improving data quality for analysis. Removal of URL versus removal of HTML tags. Removal of HTML, first we see strip out actual links HTTP that often clutter text data. Focus on cleaning links from tweets, email, and messages using regress to match, remove, and pattern that begin with HTTP or www helps eliminate external link noise. So removal of HTML tags, clean up markup languages like add division when text come from website, focus on structured tags around contents, use beautiful soap or extract only visible text, ensure readable text for raw data pages. While both steps remove the text, we don't want URL or actual links like HTTP or HTML tag are part of the web code. We need to remove both of different reasons. One of the cleaning user post, the other one scraping from websites. Removing numbers. Eliminate digits number. Numbers can carry meaning in some context. E.g. dates, price, quantities. However, in many NLP tasks, especially sentiment analysis, emotion detections, or topic modelings, numbers often do not provide semantic values. Removing numbers help reduce noise in text, simplify token focus analysis on words and contexts. Convert number to words. Converts numeric digit into textual representation, works for integrates, decimals, and even currencies with configurations. Instead of removing numbers entirely, we can convert them to words, especially when quantities matter, 2 days or 5 hours. This approach is useful for financial, medical, or logistic text, where numbers contributes to meanings. Apply spelling corrections. Spelling error, especially in informal content, can lead to vocabulary fragmentation in NLP tasks. Using the autocorrect library helps clean this noise. Work with both individual words and entire sentences, great for handling common errors in English typos. Converted characters to ASCII codes. Removal asking from the characters in multilingual data set, especially from European, Latin America, or African sources. ASCII characters are common example like cafe, Nino. These characters may cause inconsistent matching during tokenization. The Unicode library convert Unicode characters. Converting chat words to normal words. In casual communication, users often abbreviate words to save time, especially in text, tweets, WhatsApp, etc. A custom dictionary mapping is used to translate chat abbreviation into formal English. Why this matter? Improve accuracy in sentiment analysis, intent detections, and text classification. Reduce semantic ambiguity and increase vocabulary consistencies. So, by the way, you and are expanding contraction, convert in contraction into expanded form, can't or is. Constructs are common in spoken and informal written English like don't, isn't, we are, I have. While human easily understand contractions, NLP model not. Expanding contraction reduce lexical diversity, artificial caused by alternative forms. Makers text more standardized, which help downstream NLP tasks. The contraction library use these are built-in library safely and accurately expanded common contractors. So I can't move to I cannot. It it is. Stemming reduces words in base root forms like this one. Stemming is particularly useful in information retrieval, text classification, and search engines, where semantic accuracy is less important than pattern recognition. Most common portal steamers from NLTK. It is fast but not always linguistically correct. Use steaming when speed is more critical than accuracy. Working with large corpora for clustering or classification for higher accuracy, consider lemmatization, which return valid dictionary words. So running, runner, runs. Lemmatization reduces words into their base dictionary forms. Part of speech is a like stemming but smarter. It uses the part of speech and grammar rules to return the correct dictionary from a word. For example, better is not just chopped, it is interpreted as an adjective and mapped to good. It is powered by a WordNet, a lexical database of English, while stemming might turn running into run. It could also turn universe into universe. A non-word lemmatization ensures that every result is real word. Context matter, making it deals for tasks where grammar or meaning is important, like questions answering or chatbots. So here, better, good. Removal of emojis. Emojis can be removed or converted. Emojis are modern language elements that convey emotions, tone, and context. In social media or informal text, they are common, but for many NLP tasks like topic modeling, name entity, recognize text classification, non-text sentiments, they introduce noise. In this example, first we convert emojis into descriptive forms, smiling face with smiling eyes. Then we use a regular expression to remove those emojis words from the text. This helps standardize the text for machine learning models that are not trained to interpret emojis. But in some use cases like sentiment analysis, converting emojis into meaningful words like happy or smile might be more valuable than removing them. So I am so happy. Removal of emotions, converting emotion to words, replace emotion like sad and happy. Emotions are old school emotional markers made from punctuation marks like for happiness or for sadness. They are especially common in SMS, emails, chat apps, while they don't use Unicode like emojis. They still convey emotion in this step. We define a dictionary that maps emotions to their meanings. Then we replace any emoticons emotion in text with the corresponding word. This helps NLP models interpret sentiments or emotion explicitly rather than guessing from symbols. Depending on your use case, for sentiment detection, convert emotions to words. For formal processing, you might choose to remove the altogether. Combine handling of emojis and emotions. Emojis and emotion are express emotions. Many users express feeling using both emojis and emotion. For example, this is a graphical emojis. Is a text-based emotions. NLP models often treat them as noise unless we pre-process them. Here is how we handle them together. Emojis to word, emojis dematize, and then into smile clean formatting, regress, remove the turning smile into smile. A custom dictionary replaced smile with sad face. This combined approaches ensure the emotions meaning is preserved and ready for analysis. Removing punctuation and special characters. Punctuation often serves grammatical purpose but adds noise in NLP tasks. Removing it helps consistent tokenization. Reducing vocabulary size, however, in specialized tasks like hashtag or handle analysis, some punctuation may be useful or should be preserved. Hello words, let's removing extra white space, replace multiple white space with a single space. Irregular white space often comes from user generated content. Web scraping and merging text fields. Multiple spaces cause issues during tokenization or comparison. Using this, collapse all spacing into a single space while stripping remove leading trailing spaces. So this is space out, no space here. Removing single characters like A, B, X. Single letters often appear in noise text. These boundaries where only one character exists, A. This method removes those standalone characters unless they have grammatical meanings, i.e. in English, which should be preserved depending on the context. Make sure to apply further cleaning like extra white space removal after this step for tidy outputs. Big cat. Removal rare words removes words that appear only once in the corpus. Rare words, especially those with frequency equal to 1, often add noise rather than value. These could be spelling mistakes, unique identifier, or hyper-specific terms. Removing them reduces overfitting in models and simplifies training. However, this step should be done carefully in domains like medical or legal text, where rare words might carry crucial meanings. Always inspect rare words before removing them automatically. So, apple, apple 3 times, banana 2 times, and grape only 1 times. So we have apple, apple, or banana, banana, and we remove grape. Removing frequent words. Remove only common words that dominate the corpus. Extremely frequent words like the is often dominate specific words can overshadow others. This may contribute little value in distinction topics or sentiment. Removing top and frequent terms focus the analysis on more meaningful vocabulary. We caution not to remove important frequent terms, evaluate word significance contextually. So we again have a apple 2 times, apple 3 times, banana 2 times, and orange only 1 time. So here we have banana and then banana and only 1 time is a orange. Removing stop words, eliminate common words like the, is, a, reduce noise the textual data. Stop words are very common words like the, is, an, etc. They do not contribute much semantic meanings in many natural languages processing tasks. Removing them reduces the dimensionality of the future space. Helps model focus on informating words may improve performance in classification, clustering, and topic modeling. However, keep in mind context sensitive tasks like machine translation or sentiment analysis. Removing stop word may sometimes result in a loss of important grammatical structures. So we have only simple sentence testing, simple sentence and testing. Final thought, the power of text normalization. Text normalization standardized textual feature for consistent, accurate NLP analysis. Text normalization transforms messy textual input into a clean, consistent format by applying different techniques like lowercase, punctuation, removal, tokenizations, and many we are just discussed. This process is essential in NLP for reducing noise and improving model accuracy. Clean and standardized text ensure that machine learning models can interpret language data more effectively. Thank you.